In this video, we're going to talk about destructors and memory management in C++. So here we have a simple class that's been developed. There's a public integer pointer, a private integer pointer, a private int, and then a name. So let's write a constructor for this class. So it'll be called my class. It's going to take an integer parameter and a string parameter. Go ahead and do an initialization list. So name will be n, but we're going to do a little more work with a, so we're not going to use that in our initializer. And also, we don't want to necessarily modify this, so we'll pass it as a const string, just in case someone passes that value in via another variable. Okay, so here's my constructor. I'm going to have a static int counter, and this is going to be allocated in static memory. And what it's going to do, it's going to allow me to, each time a object of my class is instantiated, I can increment the counter and keep track of how many have been instantiated. Now a is a pointer, so it's a pointer to an integer, so I'm going to allocate a new int, and this memory is allocated from the memory store or the heap, and I'll initialize that to be x. And b is also going to be a new int, but I'm going to make that an array. That's also allocated on the heap, and let me initialize that. So here, instead of x, I could dereference a and reuse that. In fact, I think I'm going to go ahead and do that. And the reason is, if I ever wanted to copy and paste this code, that's probably a better thing to copy and paste than x, because x might be out of scope. So C is going to be the counter. So the first object that gets instantiated will have C equals 1, the next C equals 2, and so forth. And I don't normally recommend doing this. In fact, I strongly recommend against it. But I'm going to put a cout statement in my constructor. And this is just so we can see when that constructor actually gets called. And I'll also dereference what a is so I can see that actual value. We set up the counter, we allocate new memory for our two variables and initialize that memory. We set C equal to what the counter is, and then we have this print statement. So let's just make sure that this works. And this is going to be a very wordy example, because we're really focused here on how destructors work and constructors work. So I'll do another example with a constructor and destructor and so forth that's a little cleaner as far as the output. But I'm going to indicate that I'm going to declare my first object, and I'll say my class C1. I'll initialize that with 1 and C1. So let's actually run this just to see where we are. So n not declared in this scope 15. And then we're missing a semicolon here. Or no, that should be a semicolon, not a less than. I think that should do it. So yeah, here's our constructor. Here's the memory we've allocated. And that's good. I think we could be a little more specific about what's going on there. Let's see. Constructor C1. I think let's do A up here. I'll dereference. Well, no, I'm not going to do that. I'll do this, and then I'll. I think if I do this, maybe I'll like the output better. let's also do C here. Then I don't think we'll need this anymore. Let's see how this output looks. Again, we're just trying to get something that lets us see what that actual file looks like. And it looks like I deleted the wrong character. I believe I wanted that to be, no, I wanted that to dereference A. Again, I just want to see what, get some output that lets me know, hey, this is what's going on here. So C1, 1 there, so it's A is 1, and there's the reference, there's B, again, there's an array there, and there's C is equal to 1. So I think that's good. Maybe if I add a space here, that might look a little nicer. Other than that, I think that's reasonable enough. Okay, very good. So then let's say that's the end of declaring that. And then let's also do a pointer. And I'm going to declare the pointer. So let me save this and we'll run it. And notice we actually only have one constructor called because we never instantiate any object for this pointer. So let's rectify that. And how about instead of calling it C1, C2, let's call it main to pointer. And we'll call this main1. So instead of C1, we'll have main. Instead of C2, we'll have main to pointer. I think that may be a little more interesting in our code. Hopefully I'll remember to keep that consistent. Okay, so again, the reason for all this output is just so that we can sort of keep track of what's going on. And I understand it's going to get complicated eventually, but I want us to make sure that we understand when constructors and then later on destructors actually get called. Let's add a function to my class, a print function. Here, I think I can actually just take everything from here and copy it. But instead of saying constructor, I'm just going to say print. And then again, I should get the name of the function and it'll print the same information. I'll just see the distinction that I'm actually printing it from that function instead. Let's see if I copied and pasted this, but I've changed their name. So C1 should be main1, C2 should be main to pointer. And just to keep the lines manageable, I'll do that. So now I'm just calling that function. Looks like I didn't do main1 there. Okay, so I think that should get me what I'm looking for. Here we go. Okay, so here in main, we have some constructors and then we have some print statements. Okay, and you'll notice, no big deal when we get there, when we call that function, it does print that. Okay, so we're going to see some additional things we need to do when we're working with memory that's allocated with new. So the first thing is that in C++, unlike in Java, there is no garbage collector. So when I've allocated this memory, when the object goes out of scope that allocated the memory, that memory is still there because it's never been deallocated. So you have to allocate it yourself. So I'm going to write a destructor method. And we start the destructor with a tilde, then the class name. And there's no parameters to it. So first off, I'm going to print that I'm in the destructor. Actually, to be consistent, I guess I should just capitalize this. And that's all. Again, normally you're not going to want to have output in your destructor. The user is going to be getting rid of this object, so they don't want to hear from it, more than likely. The only reason that's there is so that we can watch and see where that destructor actually gets called. So I want to free the memory that was allocated to A. And then I'll set A equal to null pointer. Just if for whatever reason, let's say there's a pointer still to this object, you won't be able to get to that memory even if you have that pointer. And I also allocated memory if I look up here for B. So I'm going to want to delete B. But notice there, when I allocated B, I didn't just allocate a pointer, I allocated an array. So we need to use brackets on delete to indicate that we should allocate all, or we should free all the memory that was associated with B. So since B points to an array, we're going to use delete with brackets. And you can use that delete with brackets even if it's not. So it's probably a good idea to always do that. And we'll do B equals null pointer as well, just again to make sure that there's no references available to that memory anymore. And so there's our destructor. So we haven't added any new print statements, but let's see when the destructors get called. So we have a destructor after main is complete. Notice we have a destructor for main 1, but the destructor never gets called for main 2. And that's because main 2 is a pointer. So we need to explicitly say at the end of our code, delete C2. And it's not C2. I keep forgetting it's main 2 pointer now. So let's run our code, and we should see now the destructor being called for main pointer 2 when we call delete. So the destructor gets called either when a variable goes out of scope in the case of main 1, or when we explicitly call delete for something we're pointing to. Let's write a function, and this function will be outside of the class, and it's going to take a myClass object as a parameter. So we're going to declare a function in there, and we're actually going to call this func1. It's the first thing in the function. In fact, instead of cparam, let's call this funcparam. And we'll call this number 3 because that's the third one that we've actually allocated, but its name is func1. And then let's print it. So we'll say func1 print. While we're here, why don't we do the same thing for function parm, or I guess we called it param. And then that's the end of our function. So we'll close that up. So let's run, actually we'll do this before the delete. So we're in main, and we're going to call func main1. And then we're going to return. So let's make sure that we have that end there. And let's see what happens. Actually, while we've done that, let's go ahead and just print main1 again, just to see what happens. So we're missing a parenthesis there. Let's compile now. And we get a crash. So that's weird. Let's see what happened. It looks like everything worked. So here we call func main, blah, 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 end, delete, complete. And then we crash because double free detected in tcache 2. And it looked like that happened sometime when we were running the destructor for main 1, which was after main was complete. So let's go back to our function call and notice in our function call, we call a destructor. Did my end function line not print? Oops, hold on. Let me do end function here. I think that's making the output a little complicated because that's not the start, that's the end. So at the end of the function pointer, we call the destructor for func1 and main one? Well, should seem odd, right? So let's look at our function. Notice when we do this, we copy it by value. So function parm, when we print that out, right here, notice it has the same values as main one pretty much. Where is print main one? Right here. So you'll notice these values are all the same there and here. But then that's a local variable. When the function goes out of scope, when the function exits, that goes out of scope, the destructor gets called for fun param. But guess what? Function param has all the same values that main one did. So it frees this memory right here in the destructor. Notice the C value is the same. We want to be careful because what's happening is we're saying, hey, free the memory. Okay, I'll just delete all the memory this is pointing to. It's pointing to the same memory. And that's a real problem. And fortunately, C++ gives us a way to resolve that with something called a copy constructor. So let's go back up to our class. So here's a copy constructor. It's a constructor, but it's going to take a constant reference to the original thing that it was created with. What we're going to want to do, I'm actually going to copy almost all of the code from the constructor, but we're going to change it in some important ways. So we definitely want to allocate new memory for A and B, but instead of initializing them with X, which is some parameter that was passed in, which actually reminds me, did we have a default value for X? We did not, so we'll say X is 0. So instead of using X, we're going to use the value stored in original. So here we're going to dereference original A and assign that to B. And then here, instead of initializing these values, we're going to say BII is equal to original BII. And then C is not going to be counter, it's going to be original C. And I think it might make sense to go ahead and multiply this by 100, just so that we get this out of the normal loop. We don't want it to be the same, because then that indicates that we have the first value there. And even better, instead of multiplying it, if we did, let's add 6,000 to it. So then if we have a C in the 6,000s, we know that that's a copy of some other value. And we'll call that the copy constructor, which you'll sometimes see shortened CTOR. And we'll use the same format, though, that we did before. Now, let's go back and run our code again. And we still have an X somewhere. Right here. This, we're actually going to have to dereference A. And again, I would probably argue that it makes sense to do it there too, right? Because that's going to always work. We're not always going to have the variable X in scope. So let's compile and run. Now let's take a look at what happens when we start function one. So here's our original main one. Look at its address for A and B. And then when we get to our function, notice before we even do any code in the function, we have a copy constructor where that first thing, but notice the addresses are different now. And look at C, it's 6001 instead of just 1. So then when we do the destructor, we're destructing that memory that we just created in the copy constructor, and our code completes because main still has the same address as it had before. We're not freeing that memory up. So even though main was never touched by that original destructor, copies of all the memory locations it was using were, and those memory locations were freed. That's what gave us that crash before. We've alleviated that trouble. So it's always important to have a copy constructor, and also further than that, it's also important to have a overridden equality operator and some other things that we'll get into later in the semester. But for now, I don't want to overload you with too much stuff. And so I think that this covers everything we want to get, at least up until this point. We'll get into overloaded operators in the next module, and we'll talk about some other constructors later in the semester. So I'll do another more simplified example where we don't have all these print statements just so you can focus on the code. But really the point here is that with all this output is to allow you to walk through and see what's going on in the code and what's being called. Because I don't ever make explicit calls to the constructors and destructors for the most part, and certainly not in every case. And so it's good to be able to understand where these functions get called first, and then you can move on and think about how you want to actually implement those.